We will round out this module with a video on angular momentum. This is appropriate since we just have spoken quite a bit about momentum and conservation of momentum. And angular momentum is just as fundamental. However, we will not use angular momentum much until we get to the chapter on rotation, which is at the end of this semester or the beginning of the next. Nonetheless, angular momentum is very important and something that many students find difficult. And when we get to rotation, I will assume you've understood the basics, so it's appropriate to do a short review here. So assume that you have a particle that's moving with momentum p, and then we also have a frame in which it's moving. We always need to have a frame in order to be able to talk about positions and velocities. This is now its position r. So the angular momentum is defined, and the momentum L is defined as r cross p. So the cross product of its position with its momentum. And from what we know about the cross product, we can then see that if we look at the magnitude of this angular momentum, that is the magnitude of r cross p, that's going to be equal to, in this figure, this vector here, which I'm going to call r perpendicular, and the magnitude of p. So it's r perpendicular times p. So we can see then that as this particle progresses and moves in this direction with the same momentum p, as long as there are no forces acting on it, once it gets to this point over here, for instance, its new position vector, which would be r prime at this point, will still have the same r perpendicular. So we can see just from this that if there are no forces, then L should be conserved, just by looking at the picture. We can see this more formally as well if we look at the time derivative of the angular momentum, vector L dot, that is d dt of r cross p. So that's going to be r dot cross p plus r cross p dot. Now this is equal to 0. And my question to you at this point actually is, why? Why is r dot cross p equal to 0? And it's something we will discuss in class later. So L dot is r cross p dot. Now by Newton's second law, p dot is the force. So this is r cross the net force that acts on this particle. And then we can see from this directly that, of course, if there is no net force acting on the particle, then L dot is 0, so that means that L should be conserved. Now this force, even if it's present, doesn't necessarily generate a change in the angular momentum, because of the property of the cross product. If you look at the magnitude of L dot, that is r cross f net. So that's equal to r times the perpendicular component of f net. So only that component of the force that is perpendicular to r will generate a change in L dot, a change in L. In other words, if we have a force attached here, we can divide into two components, an f parallel and an f perpendicular, and it's only f perpendicular that gives rise to a change in the angular momentum. R cross f, otherwise, is known as the torque, and the book uses gamma to indicate torque, not tau, and we're going to stick to that convention. So this is the torque, the net torque that's acting on the on the particle. So the rotational analog, in some sense, this is now the rotational analog of Newton's second law. That L dot equals the torque, which of course also means that if there is no torque, then the angular momentum is constant. So we have a conservation law for angular momentum. So if there's no torque acting on a particle, its angular momentum is conserved. Now, just as we did for momentum, we're going to consider now a multi-particle system. So it consists of many different particles. I'm only going to draw 4 here for simplicity, but it could be many more. Let's say that this is the alphth particle, and there are forces acting on the alphth particle from the others. Okay. So if you want to write down the total force that's acting on particle alpha, that is going to be equal to F sub alpha, which is the sum over all the other particles. That is beta goes from 1 to n, but beta of course should not be equal to alpha because particles don't exert force on themselves. Of F sub alpha beta plus the external force acting on alpha. Now if I want to look at the total angular momentum on the system, that is the sum of all the little angular momenta, well, not 0, from 1 to n, and let's look at its time evolution. So we take the time derivative of L. That's going to be then alpha goes from 1 to n of L alpha dot. So that will be the following. Now F alpha has this form in general, but we can show, and we will in the upcoming homework, that actually the forces between the particles don't contribute here if they are central. So this is just equal to the sum over alpha or alpha cross F external, and that's then just the external course, the external torque, and that is if F alpha beta are all central. So by a central force, I mean a force that's acting a bit on two particles along the direction separating the two particles. So if we have a particle here and a particle there, particle 1, particle 2, this F12, F21, that's a central force. If somehow you had this, which is allowed by Newton's third law, then this is a non-central force. That actually exists sometimes when we have magnetic interactions between charged particles, and then this isn't true anymore. Okay, but for all the cases we're going to consider here, the forces won't be central. So in that case, L dot is just equal to gamma external. So now we can write a slightly stronger statement, a slightly stronger version of conservation of angular momentum. So if the net external torque on a system is 0, then its angular momentum is conserved or constant. All right. So let's apply this now to a specific case in celestial mechanics. You may be familiar with Kepler's laws. In particular, now we're going to discuss Kepler's second law, which states that as a planet orbits the Sun, a line drawn from the Sun to the planet sweeps out equal area in equal time. So if this is a model of a solar system, we have the Sun here in the center, we have a planet which is moving in an orbit around the Sun. Then if the time separating the planet being at this point and that point, it's the same as the time separation between the planet being here and there, and the same as the time separation between the planet there and there, then all these areas here, the areas, these little triangles here, they are all equal. That's what Kepler's second law says. Okay. Now, to see what this has to do with conservation of angular momentum, I'm going to blow up one little section like this in more detail. So draw it there. So here's the Sun. We have the planet starting out at point P here at time t, and it ends up at point Q here at times t plus dt. We're going to choose the origin to be at the center of the Sun. Now, this line drawn here from the Sun to the planet, in that circumstance, is just going to be the position vector, right? So, we have here the position vector, and we have another position vector there. So this is now the position vector r at time t, and this is the position vector r at time t plus dt. This arc segment here that's being traced out by the planet is almost the same as the difference vector here from r to r at t to r at t plus dt, and we're going to call that dr. Okay. Now, dr represents the distance traveled during time dt. So dr is essentially equal to v times dt. The velocity of the planet as it's moving here times dt. Okay. I'll write it again here more clearly. dr equals v times dt. We also have that r at t plus dt equals r at t plus dr. Now the area that we're interested in is the area here of this little triangular segment here. It has area dA. It's what's swept out by the position vector during time dt. In order to figure out what its size is, we should recall that if we have two vectors, one vector there and one there, and let's call this one A and this one B, then remember that if we take A cross B, the magnitude of that is just equal to the area of this parallelogram here that's spanned by the two vectors. So if I call this area A here, the magnitude of A cross B is A. This triangle here is just half of the parallelogram spanned by the vector r and the vector dr. Therefore, I can write that the magnitude of r cross dr is going to be 2 dA. Okay? Now dr is just the velocity times dt. So we can rewrite this as r cross v dt. One little caveat, this isn't 2a, this is dA, so that's 2 dA. So we get that r cross v, the magnitude of that cross product, times dt equals 2 dA, which amounts to saying that the magnitude of r cross v equals to twice the derivative dA dt, and that is the area that's swept out per unit time, right? That's what we're looking for. Now we can just multiply here by the mass, so we get r cross mv equals 2m dA over dt. mv is the momentum, so therefore r cross p is the angular momentum. So we then get to the magnitude of the angular momentum is 2m dA dt. So we know that gravity is a central force. It acts along this line, so the gravity acting on a planet here at point P is going to be in the direction of r. Because it is in the direction of r, that means that the cross product, the torque due to gravity, is going to be the cross product of r cross F gravity. That's going to be 0. This means then that L is a constant. The angular momentum of the planet as it's moving around the sun is a constant, and that gives us that dA dt also equals a constant. And that's the result that we were looking for. Essentially, Kepler's second law. And it's an example of conservation of angular momentum. Kepler's second law is equivalent to the conservation of angular momentum of the planet moving around the sun in this case.